Good day, everyone, and welcome to today's DevOps.com webinar. We're certainly excited that you've chosen to be with us today. Thanks for joining. Our topic today is attacking and defending cloud-native infrastructure. Certainly a lot of applications moving to the cloud, especially recently. Things have accelerated. Today's webinar is sponsored by WhiteSource. My name is Mitch Ashley. I'll serve as your host and moderator. A few housekeeping items. We are recording the webinar, and all attendees will receive an email with a link to the recording as well as a link to download the slides. So you don't have to take notes, just sit back, relax, jot down a few things, but you can just listen to our great speaker today. We also have 4 Amazon gift cards that we'll be giving away at the end of the webinar, so please stick around, find out if you're one of our winners. We also encourage questions. Our speaker today loves questions, and I'm certain he would love to hear from you and hear what questions you have. So we'll have a whole section of the webinar designated for Q&A. So let's move on to our topic, attacking and defending cloud-native infrastructure. It's my great pleasure to introduce our speaker today, Andy Martin, who's co-founder of Control Plane. Andy, let's get right to it. I'm going to turn it over to you.
Thank you very much. Right, hello everybody. Welcome to Attacking and Defending Cloud Native Infrastructure. And with that, let's see if everything is wired up correctly. It looks hopeful. Right, I'm Andy. I love to break stuff and then put it back together once I know what it looks like. I'm very proud to be an official trainer, an occasional course author for SANS. Watch out for the upcoming SEC 584. O'Reilly, Control Plane, of course, HashiCorp and Docker, and in general, Control Plane's low-level security courses, of which I'm very, very proud to be a part. I'm a founder at Control Plane, which is SecOps for Kubernetes, focusing on regulated industries, including financial services, and we espouse continuous infrastructure and security practices with a focus on cloud-native deployments. Farm to table or Git to Kubernetes. And I would like to talk about container breakouts, Kubernetes API exploits, cluster drive-bys, pwning everything we can find, and how we fix the security tie fire of the general cloud ecosystem. Spoiler alert, we do it by training the next generation of cloud-native security engineers and architects with production-like systems. We test, we remediate and harden so we can't hack back in. And there are some teaser slides from the SEC 584 course. When applications and infrastructure and security and policy are defined as code, then we can build everything with a standard set of components, ensuring reusability. We go into a lot of detail on SecOps, looking at the Department of Defense reference DevSecOps design, how we apply these processes securely to all environments. We go into third-party code risk and supply chain security, looking at the cloud-native ecosystem. Obviously, WhiteSource is a vendor that operates in this space. How do you know that the code that you're running is from the right place, signed with the right keys, from the right authors, not tampered with in transit or at rest? We also look at low-level defense of Kubernetes clusters and cloud-native infrastructure in general. And we go through some detailed models of the system. With that, there is another angle we have here. The KubeSim Kubernetes hacking and hardening simulator is incorporated throughout the SANS course, and is also available as an open source project at the link below. So with that, what are we going to do today? We're going to try and burn some things. Because of various misalignments, I will not be doing all the live demos, but all of these things are recorded, and I will link you to the live demos to prove that these things are actually possible. So what have we got? We've got Docker and Kubernetes. We love Kubernetes, but actually we find it perhaps a little bit difficult. It is a distributed system, and distributed systems come with their own set of problems, partial guarantees, and emergent failure behaviors. So what's the actual problem here? Well, we are looking to layer our security when we're running in Kubernetes. If I can get into a container in a cluster, I will probably start trying to escalate privilege and dancing through infrastructure or whatever is accessible in order to get to a state where I have an asset, a desirable thing that I would like to exfiltrate. So containers are awesome, but they emerge from this primordial kernel soup, a child of evolution rather than intelligent design that has been morphed, refined, and coerced into shape so that now we have something usable. But don't forget, containers do not exist. They're merely the resultant bundling and isolation that's left over once a kernel has started namespaces, configured C groups, added Linux security modules like AppArmor and SE Linux, and started our precious little process inside. And finally, all that being said, we love containers, and of course we do love Kubernetes, despite spending this time looking at some of its failings. Frankly, we're only here because it is such a fabulous and configurable system on which to build. Okay, so let's remind ourselves, we are looking at the Kubernetes orchestrator and the low-level details of the interactions between these components. So this view of the cluster architecture includes the protocols used to communicate between components. I, as always, have Lucas Calderon to thank for this fabulous diagram. All communication, as we can see, goes through the API server in the middle of the diagram, which is the only component able to talk to etcd. etcd is a distributed, reliable key value store where the cluster state and sensitive information is stored. Then we have controller manager and scheduler, ensuring that requests to the API server eventually run on kubelets, and the kubelet itself interfaces with the container runtime on each node, and a container networking interface for cross-node communication. And then finally, the kubelet will start the container itself. We have various different protocols in use, and we will be referring back to some of this later. So more questions here. Where can we attack the orchestrator, workloads, infrastructure? There are plenty of things that we can get to in Kubernetes. And really, once an attacker has remote code execution inside a container, as I mentioned, they will look to enumerate and find options to escalate their privilege, either within the container itself, perhaps going from an unprivileged to a privileged or root user, via accessible services, so other microservices, maybe system services running on the host, databases, stores and queues running on the periphery or in the same subnet, or just routable, frankly, and cloud provider metadata APIs especially. And once we have those network endpoints or even just shell endpoints, we may try to stuff credentials, inject code so it's executed out of context, exploit CVEs that we may be able to determine from banners, or again, we're just kind of brute forcing, with the ultimate goal of further remote code execution. And at that point, an attacker may choose to utilize their remote code execution to mine cryptocurrency, which is a little trite at this stage, frankly. Nobody really seems to have got away with a significant haul of cryptocurrency, potentially due to block sizes at this point. Or more interestingly, perhaps add the pod or node to a botnet, as we saw with Ian Coldwater and Brad Giesman's talks at RSA and KubeCon last week. Potentially use the access in the pod as a jump point to attack other targets on the internet at large, or frankly, just going after the crown jewels in your organization, be they data or algorithms. So with that, what should we not be doing? We know these are bad, right? These are just the basics. Running a privileged container is equivalent to running its root on the host. At this point, the container is only a tarball distribution mechanism. The host is not isolated from a malicious user in the container. Some monitoring and security applications do still need this, but usage should be appraised carefully. Secondarily, the Docker socket gives us write access to spin up new containers, and this is a similar attack vector. If that new container has the privilege flag, well, then we're just seeing a repeat of the first attack here. Rootless builds go about this a slightly different way in terms of sharing the Docker socket. Instead of creating another container in which to build the container image that's specified in the Docker file, the new glut of rootless container build systems use one of a few different mechanisms. One is to unmask the proc file system. So a container is not a complete abstraction, and part of the work that a container runtime does is to prevent the true read and write properties of the proc virtual file system, which is just a shim to kernel internals, from reading and writing as you'd expect them to. So for example, it's possible to spin up a child container using proc. It's not possible to do that if we're using a standard hardened container. If we specifically, I say hardened as in the container runtime, but if we specifically unmask proc, we can spin up child containers. And this is how Canico works. It's how a number of the other new breed. That's better than all the above options if we're in that position. There are still compromises. We can still be using user namespaces, which have their own set of compromises. Suffice to say, we need none of these options. Yes, so ye olde UID 0 gets us close to root on the host unless we run a rootless runtime or user namespaces, which we're getting to in LexD and Podman and the Run C release that will be out this year, the next edition. So those are misconfigurations. Let's see what happens when we run containers on old kernels. Again, we can pop these things out. So in a container's lifecycle, unit tests to run in isolation on a container without any network testing. Linting broadly under this model that I'm proposing here, it's not a solid abstraction, but broadly to map the concepts onto, I think it works. Linting I would put under unit testing and testing the configuration of the pod. For example, how is Docker Compose set up? How is the Kubernetes resource YAML security context configured? Comes somewhere in between unit and integration. But we'll say config testing is also static analysis, unit testing. By extension, integration tests are run with mocks and stubs, and Docker Compose offers a lightweight way to stand up a stovepipe of a distributed system. Minikube and remote clusters are other options, depending on the memory and compute requirements of the application. And then we should bake our test data into Docker data volumes. This saves confusion if we're running Docker with a nested Docker socket, which is the old school build style that we still see. And of course, then end-to-end tests under this model are system acceptance tests. Canary deployments may be using something like Flagger and Istio, allow parallel deployments of the latest version of a service alongside its current version. So why do we care about this? Because there are ways for us to lint our Docker files. This is a way of introspecting our run commands and ensuring that shell check passes, that we have an opinionated introspection on the contents of our Docker files themselves. We're checking for things like version pinning in our application repositories, in our distribution operating system repositories, directive validation, so making sure our entry point is correct, looking for strange bypasses like Unicode non-breaking spaces. It can be fun to try and hide commands and other commands. Don't abuse the cat, other shell check bits. So it's strongly recommended to run something like HaloLint here inside the container. What will this detect? Well, this can tell when we're running things as a root user, when we are setting incorrect bits, etc., like running setuid. And this gives us a nice uniform interface by which to protect ourselves from errors within the Docker file itself. We have multiple layers here, of course. We have initially the Docker file to build the OCI container image, but then we have the runtime configuration. It's still OCI, but instead of being the OCI image, it's now the OCI container. And that OCI container has Seocomp attached. It has an app armor profile. It has a security context. It is not running as privileged. It is not running with host networking, for example. So we have two different parts of that configuration. Initially, we test the image configuration, but then at runtime, we want to test the resource configuration, how that image is run as a container. kubesec is, again, an opinionated control plane grown tool. very much a precursor to OPA. So you can think about it in the same gamut of tooling again as OPA, as the pod security policy. This is static analysis of configuration. Why is this a good thing? Because everything is now declarative. And as such, we have a consistent and uniform interface. And we know that if we've turned on too many host network shares, for example, we're kind of equivalent to running as privileged. So we want that degree of introspection and really the spectrum of introspection, if I can pronounce correctly, is we start with pod security policy, which is very granular, binary, is this thing on or not, a little bit of depth and things like the volume types. Then something like kubesec, which just makes an opinionated call above pod security policy, determining or offering a view on the ultimate risk. So a single risk score for running an entire deployment or a pod-like resource. And then you have something like OPA or gatekeeper, whereby you write your own policy or you consume a policy somebody has written, which allows, I guess, during complete introspection for a static analysis and configuration testing language. So really OPA is the gold standard, and we hope will replace pod security policy as pod security policies become deprecated, and then kubesec sits in the middle. Here's an example in secure pods, and you see it offers some rationale and some recommendations as to what to do to fix things up. Why do we care about this? Because we can smash the isolation of a container with a poorly authored security context. All this stuff is bad. We don't want to run as root. User namespaces are not enabled in runc or in Docker. They are not enabled in Kubernetes. Can we run them? Yes. Is it especially difficult, and do a lot of our pods or the container images break? Also yes. So if it's possible to run them and author your own Docker images, so your Docker files, to take advantage of user namespaces, they provide a useful boundary. But because they're a cross-cutting concern across so many places in the kernel, and a lot of kernel code was written with the expectation that root would actually be UID 0 in the host user namespace, they've historically been the source of some privilege escalation vulnerabilities. That means that running as root inside the container is not translated to anything outside the container, it's still root. While this is not a security vulnerability in and of itself, it does mean that other vulnerabilities could be more easily exploited because the capabilities afforded to the root user are much greater, even within a container, to those afforded outside. For example, mounting host file systems. Other things we don't like, privileged containers, because that turns off everything except for a virtual or a shim PID namespace. Seocomp and app-on profiles. Again, Kubernetes does not ship these by default. Docker does, which gives it a useful hardened security context. Some of the things that it drops, for example, are 32-bit system calls. We don't need them. Why should we have them? Historically, they are a source, or perhaps they're more likely to be a less well-maintained API, and as a result, possibly more likely to be susceptible to 0 days or unknown errors. So just for a risk-based judgment, Docker dropped them. Kubernetes, on a developer adoption judgment, decided not to, I've actually inverted that, haven't I? Docker dropped the system calls by applying the Seocomp and app armor policies, whereas Kubernetes decided that developer adoption was more important, and by any metric, frankly, has won that comprehensively. Other things we don't like, just giving away full RBAC. Host volumes allow breakout onto the host. Sharing namespaces is always a bad day. It should be noted that the network and IPC namespaces are actually shared by a Kubernetes pod that is part of the pod abstraction. But in this case, we're actually talking about sharing those with the host. So again, breaking that abstraction or the isolation. Privilege escalation within the container allows the non-root user to become root. Capabilities are a useful way of reducing the privilege set that the root user has. And C groups are not actually a security boundary because it's easy for a process in a C group to remove itself. They're not designed as as a strict isolation mechanism. However, they are the only way that a developer can communicate their intent to the orchestrator at runtime. So if we set a limit, if we set a request, what we're saying is, I will use no more than this total amount of C group space, so you can pack 10 of me onto this node. Whereas if I've got a request that's higher, it's actually saying, I would, that won't quite work, will it? If you have a request that's lower, rather, then you're saying, this is the most space that I want to take. I might use some more, and then Kubernetes will probably optimistically bin pack as many workloads as it can manage. Without those things, we're just constantly spawning processes on a machine, and there is no way for the orchestrator to usefully pre-provision memory. So while they're not dangerous from a security leakage perspective, from a denial of service perspective, they are entirely relevant. Okay, so obviously I love testing. There's some dynamic testing we can do at the unit test level. So first of all, we're talking about static analysis. Now we're talking about actually executing the container image. So container starts, and then exercising the code within. What can we do? Well, traditionally we would use inspec or server spec, which are just kind of in the same direction. Server spec's assertion library is actually a bit narrow, but both of these require Ruby to be loaded inside the container before the container can have some form of assurance run, let's say. That's not really a good look, especially if you're running, say, a Java-based application or even a static Golang application, because then you need all the cruft that comes with an unlinked binary, basically. No, sorry, a linked binary. So you need to use libc in a container. You have dependencies that the operating system should provide to you. The foil to this is GOS. Simple, declarative, highly parallelized, and written in Golang. So it's a single static binary that can just be dropped in alongside others, or irrespective of what technology is within the container, just dropped in alongside it. We can format the output in JUnit tap RSpec. It is YAML based, so it's a declarative interface to the test suite, and a 10 megabyte single self-contained binary, which can also function as an HTTP health check endpoint for Kubernetes. That is cloud native, ladies and gentlemen. Here is an example. Command is the type of test. Then the next key Java version is the actual command to invoke. And in this case, we're looking for standard error to match OpenJDK 1.8 and a 64-bit JVM. This is useful for ensuring contracts with upstream base image providers. We can pin version dependencies in our own doc files, but if we're consuming something from upstream, we would like to know when something breaks before we end up shipping versions that we don't necessarily expect. And of course, the compromises here are the same as version pinning in doc files. It can be used to have fully deterministic builds, but pinning dependencies has maintenance overhead. Okay, so that was a little bit of testing to try and get around some of this stuff. What was Dirty Cow? Well, 4 years ago, there was a Linux kernel bug, which gave root on every kernel since July 2007, which was quite a lot. It is a race condition in the kernel's copy-on-write implementation of private read-only memory mappings. And this was applicable to everything that ran Linux. Embedded devices probably have had no path to upgrade and remain vulnerable. An exploitation of this particular attack left no trace of any abnormalities within system logs. The mitigation, as with so many things, is to upgrade, run the latest kernel version. This bug was almost patched in about 2006, but had side effects, and they rolled the patch back. And then undoubtedly nation states were taking advantage of this. It should be noted that being a kernel bug, it's exploitable from any unprivileged user on a vulnerable kernel, but it's also exploitable within a Docker container. I say Docker container within a container. The reason for that is that there is a single shared kernel between all containers on a host, and that means from within the container, I can then attack the host kernel because I'm sharing with it. Of course, virtual machines still use the host kernel everywhere we're using KVM, that is a kernel virtual machine. But this particular attack vector was a particularly nasty one. The gentleman, oh, I apologize, I haven't actually advanced the right slides. There we go. This is the dirty cow. Take a moment to appreciate the glory of the marvelous logo that they have. Logo vulnerability is still very much in vogue. And the gentleman who determined that this was an in-the-wild attack was running a rolling packet capture. So all traffic coming onto his server was being captured and persisted. And when he discovered unusual activity in his honeypot, he pulled that binary code out of the TTP session and reconstructed it, tested it in a sandbox, and submitted it to the Linux kernel mailing list, which is an excellent community-driven piece of work, and we all owe him a huge debt. So why is Dirty Cow bad? Well, containers and default configurations did not contain this bug. We rely upon the kernel for protection, namespacing, C groups, invocation of security extensions. These are all in the kernel. If the kernel lets us down, there's nothing we can do. To some extent, we can actually reconfigure the kernel in bizarre and wonderful ways. One of the things demonstrated in, I'm not sure which version actually, but demonstrated last year was stacking LSMs. So that means AppArmor in AppArmor, potentially in AppArmor again, well, I think the demo is only twice. The purpose being the first AppArmor is the interface to the application. If there is a bug there, the second AppArmor is the interface to the first AppArmor. And as a result, you shouldn't be able to exploit the same bug twice. More work on that is required, of course. The Linux Plumbers Conference is on this week for those with an interest in that particular thing. Yeah, very strongly recommended. Excellent, excellent conference. So, of course, thanks to all the kernel developers who are doing all the hard work and occasionally make mistakes that then generate this sort of global panic. So, as a reminder, all system calls inside the container hit the host's kernel. There is no kernel inside a container. There is a non-deterministic live demo of this available on YouTube. It is a little bit long, but even though it's non-deterministic by virtue of being exploiting a race condition, happily it does work. And just to briefly paraphrase what happened in there, it is a container security escape. We get root on the host from an unprivileged user inside the Docker container. What's the answer to this kind of attack? Just to harden our containers, frankly. Excuse me. Yeah, we need to harden our containers. And the way we do that is with security contexts. Again, this is the runtime configuration that wraps the container image when it starts into a container and is to do with the way that the container runtime has configured the interface between the container and the kernel and the networking around it and the storage and other ancillary functionality. There's quite a lot here and I won't go over it again. We can see again, Seocomp is enabled by default. Sandboxing, there's a whole tranche of new isolation technologies and sandboxes. We see gvisor, Firecracker, Cat containers, the Rust VMM library. I did 35 minutes of equally breakneck communication at KubeCon last week. If you're interested in those things, the talk is called "In a Container, Nobody Hears Your Screams: Next Generation Process Isolation." And I guess it's not out until the KubeCon talks are live at the beginning of September, so not too long. So yeah, broadly discretionary access control, how we configure the file system, the capabilities, never enable caps sysadmin. It is a bucket enabling everything. We're about to see, well, we have now seen 2 new capabilities to gate the BPF functionality that things like Cilium and anything that Brendan Gregg consume in terms of consuming that capability, which will dilute the privilege of that caps sysadmin bucket again. Then we have our sandboxing and finally mandatory access control. Mandatory access control is mandatory rather than discretionary because it is mandated internal to the kernel. So a discretionary access control is, what do you think about giving Bob a view on Alice's files? Well, Bob's not part of Alice's group, so at Alice's configured discretion, it's a no. Mandatory access control is more like thou shalt not view this file, open the socket, use this protocol. So it's far richer interface than just what we're used to. Okay, onwards. The Seocomp we have in Docker, we have to thank Jesse Frizzell for, who is the Wonder engineer who shipped a huge amount of container-based security functionality, first for Docker and then secondarily for Kubernetes and GKE. We won't go into this too much, but as you can see, there are useful things in that Seocomp profile. We don't want a container to arbitrarily clone new namespaces. Why might that be? Well, because we can then clone a namespace, enter that one, and we have none of the same security boundaries configured on the new namespace, and then we're just getting closer to the host. So at all times, every time we're closer to the host, we increase the risk of running that process. The process may not be fully trusted, it may be sensitive. Nevertheless, no matter how it's configured, no matter what it is contained, no matter what the container process is or has access to, maintaining the isolation boundaries of a container are really core. They're the key container security strategy. Okay, so a little bit on writing effective Seocomp profiles. Frankly, this is how container security applications work. If we do them statically, we can hand author our profiles. That requires some low-level interface awareness. We need to know what system calls are we using? Why would we be using them? And we're probably at that point somewhere towards a C or a kernel developer. And that level of artisan policy authorship is a little unusual, let's say. So more generally, we use dynamic analysis. That means we watch the runtime behavior of a process inside a container, we capture metadata about it, and we then deny access to any of the system calls or file system points. In Seocomp's case, just the file system calls, sorry, just the system calls, because Seocomp is uniquely an interface for kernel API and system calls rather. And then we deny access to everything else. So if we're using, a Twistlock or a Prisma Cloud as it is, or an Aqua, this is part of the enforcement that they do. It's not the whole piece, but it is a useful piece. Okay, let's look at some container security controls. Thank you, Bruce. What do we have here? Okay, so AppArmor was bypassable, and this is a tremendous, I hesitate to call it a hack. It's just configuration bypass, and it worked because AppArmor has, again, we're using this proc virtual file system. This is an access into the kernel, an access point, and it's somewhere that we can read and write data. So when we see at the top of this Docker file proof of concept, touch rootfs, okay, that's just, we're creating a file system on disk outside the container that will add into the container. So touch rootfs at the proc self file descriptor 4 and 5 path, and at the status and attribute exec paths, we are turning those into volumes. So what does that mean? It means that we are adding a file system at the root of this busybox container. We're then declaring it as a volume, and then at runtime, when AppArmor goes to read the configuration, saying, am I configured? Am I enforcing within this container? The container lies to it because it was able to mount these flat files over this virtual file system. This had existed for many years. This was 22nd of September 2019. So as with all code under active development, or even recently under development, there will always be bugs in these things. And even applying our security controls requires a defense in depth approach. Why do we have Seocomp and AppArmor? Because even though they intersect and do slightly different things, they are still useful where the Venn diagram overlaps in the middle. So yeah, not a critical bug on its own, but should get a CVE assigned. Perhaps generous wording. What else do we have? Proc self exe. So this is a bug within the container runtime itself. And as you can see, the contents of this proc virtual file system really are fabulously juicy and interesting. So in this case, if we go /proc/process number, we're able to see information about the process. This is a bit like running PS and then the process number, or PS -E maybe, I forget, but they're probably -P. But anyway, in this case, self is a symlink to the actual process, or a magic link, and exe is the executable running. Now, of course, proc doesn't copy executables into itself. These are pointers to memory, pointers to inodes. What happened in this case is a malicious program running inside the container was able to follow these symlinks, which were available to it from within the container. So the symlinks that the host should be consuming, but the container can work its way down to them thanks to this bug. At that point, proc self exe pointed to the runc binary that started the container. What did this mean? It meant that the container image could run a process that would patch the runc binary on the host. What does that patch do? What would you like it to do? Let's run everything as privileged. Let's drop a reverse shell from root on the host. So at this point, we've just bypassed any further container escalation. We're just going straight to the host. It's root access. It's a root remote code execution. So again, runc has existed now for 6 or 7 years, maybe a few less. And here we are still finding bugs critical bugs in the hot code path, if you like. So these things are complex. They've been evolving for many years. And again, the lesson is relatively simple. Keep everything patched. We really care about the kernel. This is the comparison with VMs is similar because with everything in KVM, we're still looking at that kernel-based security boundary. The reason I'm harping on about this and belaboring the points is because, as the talk I did at KubeCon mentions, the line between containers and VMs is blurring. And really what we're ending up with is a load of kind of, I would say interstitial, but it's not that. It's we've reached the evolution of this thing where we are, for example, for Firecracker, we're starting a process, a virtual machine manager that starts a VM, and then we wrap the virtual machine manager with a container. So we use namespaces, we've wrapped Seocomp around there. Now, it's not literally a container, as you'd expect from an OCI container, but it's all the same technologies. So the spectrum is becoming increasingly bright and blurry, and exactly the same thing applies for containers as VMs. They use most of the same code paths within the kernel. It is only some of the runtime behavior that differs. So containers don't exist. VMs exist in some form, but again, kind of ephemerally and not the same way. And as the reputable track hosts from FOSDEM, Container Room this year, put it, containers are a user space fiction, which I think is glorious because they're constructed in user space out of bits and bobs and tooling that the kernel makes available across a huge range of APIs. And the reason Docker is successful or was successful was because it offered a wonderful developer experience on top of it. Yeah, back to the emergent property of a collection of stimuli and restrictions. And then, of course, a lot like consciousness, potentially. These things were not intended at inception to be an isolation boundary in the same ways that virtual machines were meant for process sharing and not necessarily protecting the memory that those processes used. And then we see this evolution of use as the technology advances to fit use cases and then users push at the edges of those technologies. So yeah, that's where we are with containers. And we'll invoke the young lady and the portal cube just to remind us, is there a lesson here? Well, not really. But everything is held together with string and sticky tape, and we need to be aware of these things so that we can build the appropriate security controls. And so, what do those controls look like in this case? Testing is a dark art, but we should be applying our security test suites to everything that we can see or find. Anything can be a security test. Start with clean code, the Uncle Bob style decomposition. Nothing changes with security testing. If we use a library that people understand, my personal shill is for the BAT's core bash testing library. You can test anything with bash, and a test library in bash is possible. It may amaze and amuse you to learn. We can use things like PyTest. We can use whatever we have provided to us by things like RSpec or Behave. Personally, I kind of shy away at using compiled languages for this, because the number of operations and security engineers who can contribute to cloud native read Golang or Rust. I doubt you'd use Rust at all. Test suite are vanishingly small, and really the problem here is not writing the thing in the first place. It's keeping it maintained as requirements are updated. The system is used for different things as it naturally evolves with business requirements. So the choice of test library in these cases can be important. We use our traditional arrange actor certs, set things up, do a thing, make sure the thing was the thing we wanted it to be. And of course, we need to also, when we're writing our tests, test the inverse, make sure that our selectors and matches actually do something. As before, I go into a lot of detail about this on the various security training courses that I do that are more than a couple of days. And of course, control plane are firm believers that DevOps and DevSecOps are just sound engineering. Sometimes labels and movements are useful to spread concepts and encourage adoption, but if DevOps is not fundamental and foundational to the approach of an operations team, a security team, an entire project, fast-changing security requirements will not be easy to implement, and we will end up in the classic delayed remediation cycle, where most organizations are happy to go on record as saying that they have a 60 to 90-day remediation time. That's just not good enough, frankly. With cloud native, everything can deploy very quickly. We're built upon CI/CD principles. We're built upon blameless postmortems and rapid cultures of experimentation. All those things segue beautifully into DevSecOps, but without the foundations, it is a lost cause just trying to jump straight in my experience. So we looked at a lot of things just then that were frankly just out-of-date versions. There are mitigations that are not just update my kernel version, but they are all, again, sort of rubber band. What's the word I'm looking for? Plasters, I suppose. They're just plastering over the problem. If we're applying a Band-Aid, there we go, excuse me, Band-Aid solutions. Ultimately, we would always look to stay close to the latest upstream version. And of course, with some risk window, because we don't want to be early adopters. We have the bleeding edge, we have the cutting edge. We probably just want to maintain some sort of freshness rather than be installing new Kubernetes versions on day one. Consuming a new version release from an open source project in GitHub. Those things just don't make sense to any risk-averse organization unless we're waiting for a security fix or a patch, and then we need to decide, do we really want to be the first ones to test it? How long can we wait? And then we're relying upon the quality of our intrusion detection and monitoring systems, and of course our security team to quantify what the risk actually is. And onwards we go. So yes, just a little bit more. We can actually use GOS in here again. GOS is Go Server Spec. It's not the ultimate test tool, but it's pretty good. And this is what happens when you paste a static GIF instead of an animated GIF. I think I should have referred to that by URL instead of image, but nevertheless, there is a very quick path if you follow the link here to automatically add file system state into a GOS file. And that means creating test suites becomes very quick and easy. Testing is cool. Without testing, we can't prove we're secure. Of course, testing never really proves the absence of bugs. It proves the absence of regressions that we have tested in a comprehensive manner. it's mealy-mouthed, and again, it is a dark art. We're just doing the best we can, but not writing so many tests the system can never be maintained or upgraded or otherwise usefully worked upon in the future. As I like to stand on my soapbox and beat the drum and fly the flag of, testing is a dark art and a learned discipline and requires software engineering expertise to be guided and a healthy skepticism to prevent test fixation where everything becomes a test. The test-driven argument of does it guide the interface or is it applied afterwards? It's really nice to apply the interface, but sometimes guide the interface, but sometimes we don't actually know what it is we're building, and how can we extract an interface prior to constructing the actual application itself or the interface code. It's the same thing with DevSecOps. Yes, we can do accept and test-driven design where we make sure that our network is not accessible from a third-party location, and we can run that during development to make sure that we don't Terraform open our security groups or stand up load balancers that we don't want to do. So just an aggressive nmap, for example. But then the minutiae of how the routing works internally, of what services should be accessible, layers 3 and 4 with network policy, layer 7 with Istio, we probably don't know all of those things until, well, actually, maybe we do need a communication between these things. And we're in the kind of a waterfall agile balance where we do try and plan up front, but not at the expense of agility. Okay, so those were too easy, apparently. There are things on the public internet that we can also have a pop at. So we're going to find the public cluster to attack. How many insecure Kubernetes hosts do you think we can find in a few seconds? 10, 100, 1,000, 1 million? It will be a lot. Of course, this may not be legal in your jurisdiction. Technically, it is not legal in mine. And so, of course, I haven't done it. But this platform has already port scanned the IPv4 address space for us, indexed all the content, and preemptively attacked it. It's kind of knocked on some of those ports and just checked what banners are being returned. And if things are unauthenticated, assumed that it's an open API, and then pulled back some, for example, Kubernetes pod manifests from API servers. Please do search for yourselves and ensure that you are not present. So here we are, but this is what we're searching for, Kubernetes, no auth, and there we are. So there was, if we look at a server that's actually up on Binary Edge, what do we see? Normally that it's leaking version information. So that the presence of the anonymous authentication flag allows an unauthenticated user to hit the /version endpoints in Kubernetes. This returns version information. We would not let our version leak if we were running Nginx or Apache because we've been conditioned. Attackers will use anything that we leak in order to go and search CVE registries and look for matching CV to version correlation. So we know to reduce useful information, and really we should just be disabling and allow anonymous auth. It's not, unfortunately, really that easy because some applications still rely upon anonymous authentication into the kubelet in order to check health checks and things like this. We're almost out of the woods on this, but it's still not absolute. And I would urge you to not only test it in your clusters, but also have a sufficiently robust test suite that verifies that your control plane, the Kubernetes cluster, and the workloads are functioning as you expect before and after that sort of change, because it may take a few minutes to light up like a Christmas tree. So I have a useful nmap script here to basically test API servers. If you run this script against Kubernetes endpoints, it will tell you whether it's Kubernetes or not and whether it's got anonymous auth disabled. Right, and there are other things that we can do here. Of course, there was an MTLS attack where poor error handling in Kubernetes allowed essentially an unauthenticated user to execute API calls as the API server. which meant an abruptly terminated WebSockets connection would remain open because the TLS tunnel was open around it. The WebSockets connection went through that, but when the connection broke, the tunnel maintained, or it stayed open. And because Kubernetes is a TLS-based or mutual TLS-based zero trust system, the presence of that tunnel was enough to allow attackers to upgrade their privilege, if you like. Yeah, so again, lots of fun there. These are, yeah, again, all things that we should be avoiding. What could we do? Well, we could crypto mine. I think actually probably that attack has lost all of its bite. Really now what we're worried about is crypto jacking or crypto locking, where all of your assets are frozen. I've got a Garmin watch. I don't know how much they paid to have their systems decrypted recently. It's actually, in some political leanings, it's actually illegal in the US at least to pay a ransom. So far, we've seen no legal cases brought for companies actually paying ransoms for their entire data estate. But suffice to say, there are kind of shady middleware companies, middle brokerish companies that will actually do the payment for one. But yeah, nevertheless, if the service that's attacked has write access to a database, we're vulnerable. We can also lock people out of clusters, delete the nodes, but I mean that's not so elegant an attack. Yes, tinfoil hats are cool. Just we shouldn't be running API servers in public. It's a privileged API, and the fact that the API is authenticated has never been a good reason for us to put anything on the public internet. We put SSH hosts behind a Bastion server because we don't trust the SSH. I mean, we've seen bypasses, we've seen attacks. And so by extension, we keep our private APIs and VPCs, we firewall things, we IP whitelist because we trust but verify. We should never be just issuing the verification in the name of zero trust, because zero trust does not mean put everything on the public internet. Defense in depth, network segmentation, trust zones for different data classifications. We do these things not because we like them, but because we have to. And Kubernetes is no different. We shouldn't throw away the lessons of the past just because we've run wild amongst the glorious halcyon meadows of our broad and delightful cloud native future. So what else have we got? Well, if we really want our Kubernetes API servers on the public internet, we should be ready for the billion laughs style attack. Thanks to Roy McCune, Brad Giesman in Coldwater, and pals for discovery and exploits. You may have heard InfoSec Twitter honking. It has a not insignificant amount to do with this. It should be noted that any string will do in data key A here, but the honk has been emphatically recommended by the authors. So what's the deal here? Well, sorry, I've actually advanced the wrong slide again. Billion laughs once more. Here is the honk to which I referred. I should just let that rest for a moment. And anything in this YAML object in key data A will do. And this is just a Kubernetes API request. It is a self-subject access review, which just asks, can I do a thing? In this case, the thing is, those of you that recognize, it is a recursively forever expanding YAML document. And that is because ampersand A is a reference. And so it's actually referencing itself. Sorry, it is the reference, and then the pointer in all the A's means that it's just referring back to itself, and we have this monstrously explosive and recursive. It's equivalent to a fork bomb or a zip bomb or something like this, but it's just in YAML. And as I was trying to say, this is another open API problem. We're dealing with the fact that we did not have secure by default configuration in Kubernetes to begin with. And then deserialization attacks like this can occur again with the system anonymous role able to perform the self-subject access review stuff API subsection. And yeah, of course, we just update. So with that, that is where we would put our billion laughs. So in order to take our private endpoints off the public internet, we can use something like NetAssert, another control plane sponsored project. This is just nmap for cloud native systems or bare metal or virtualized infrastructure. It's basically a way to attach to all the network namespaces of the containers or the pods under test and fire TCP or UDP or eventually Istio the TLS requests to other DNS names or IP addresses and determine whether the port is open or closed. It's very simple, but network policies operate in a union fashion. So the more network policies we add, the more difficult it is to reason about these things. And yes, thus was born.
Hi, Andy, it's Mitch. I just wanted to time check with you. We have about 4 minutes left. Okay.
Sure, thank you very much. Okay, we are just about at the end. We have some BATS core to go in here. I will just zoom through the end. So BATS core is the testing library I was shilling for earlier. Let's get back in here. Excuse me. We can also break out of service meshes. I've never quite had enough time to demo this part of the talk because it does go on a little bit long, for which I apologize. There are mechanisms to attack service meshes. I'd be happy to go through if people are interested. One of them is the insecure admin ports. Lots of stuff in there. We should be securing things and running intrusion detection. And then finally, we can actually bypass some of those things in Kubernetes. Simulator is our safe space for testing these things. It teaches attendees or users how to break out of Kubernetes and then how to harden it again. And it's all open source, or we're happy to train you on it as well. Finally, everything is just a process. Harden everything, test everything, and avoid false positives. Finally, ensure that developers can actually test these things so that they have a useful way of doing stuff. Always be prepared for somebody doing something quite untoward. Sec 584, which covers all this and more in exhaustive detail, if you're not exhausted already, is now in beta and will be available more broadly next year. And with that, with moments to spare, 3 minutes, I am done. Any questions? And thank you for your attention.
We do have some really good questions teed up. We certainly won't get to all of them. One, I just want to summarize. Could you, I know you hit on several things today, but if you had to mention 3 or 4 best practices for securing containers, Kubernetes, what would you recommend?
So a lot of my work is with regulated industries, and as such, I'm very concerned professionally about supply chains. So at the moment, the provenance of the container supply chain is pretty wild. We install stuff from GitHub. We just pull whatever application dependencies are required from Ruby gems or PyPy or NPM or Maven. We probably consume base images from the Docker Hub without validating them. We definitely run any old image from the Docker Hub. So being more conscious, looking at things like Notary V2 is coming soon, in Toto, which is build stage security and distributed builds, Grapheus, which is build metadata, Kritis, which is GCP's implementation. Those things are all super interesting to me and highly relevant for untrusted third-party code. From a very simplistic level, we can all run IDS without any problems these days. Stuff like Systrix Falco is a really nice way of observing what's running in the cluster and taking remediation steps. So yeah, I really love those. And configuration testing. So basically what I've just highlighted there is it kind of doesn't matter how bad your container image is if you're testing the configuration, running intrusion detection, and also trying in some way to prevent yourself from being hosed directly. Well, you've really reduced the risk of running a thing, because most of the problems we see with containers are misconfiguration based, accepting some of the upstream supply chain. So if we can test for and guarantee to some level of certainty that we are not shipping privileged host network, host volume mount containers to production, and then we enforce that with admission controllers, we're going to be in a much better place than the average.
Great. I think we'll have to leave it at that. Instead of speed reading the credits, I'll just jump to the winners of the gift cards. Winners are Frank D, Troy D, Jared S, and Jill S. And the folks at Media Ops will get a hold of you about getting those gift cards to you. Questions that we didn't get to, we'll give them to Andy and help him get those questions answered back to you. So thanks for your time today. Thank our guest, Andy Martin, co-founder of Control Plane, for his great presentation. So have a great day, everyone. Be careful out there.